So sometimes cubing or squaring x or taking the root of y, sometimes that doesn't work very well. So another method that you can use to straighten out relationships is taking the logarithm of x or taking the logarithm of y or taking the logarithm of both. This right here is just kind of the mathematical reason for why this helps to straighten out the relationship. But really all you need to know is you could do one of those three methods to try and straighten out a relationship, but they will tell you which one they've done. For example, here's the same data that we looked at, right? And now here's the original scatter plot. They took the logarithm of the weight, you can see here, and they took the logarithm of the length and they re-expressed it. So here it says it, log of the length, log of the weight, and look, you can see it looks linear. And they gave us a scatter plot to go along with it to see if there's any hidden pattern in the residuals. So this is the same data re-expressed for the third time. Based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length for the Atlantic Ocean rockfish. So how do we justify if a linear model is appropriate? We look at the scatter plot, it looks linear, it looks strong, and we look at the residual plot, and there's no obvious pattern. There's even scatter in the residual plot. So the linear model looks fit, looks like a good fit. So the scatter plot has a linear form and the residual plot has a fairly random scatter of points about the residual line 0, which is this line right here. It's just showing this, any point on this line or residual of 0 would be on the regression line. So the power model seems good. Give the equation for the least squares regression line. So here it's the same deal. Coefficient of x, slope, coefficient of the constant, y-intercept. But now you have to make sure you're saying the log of the weight and the log of the length. So that's what we're doing here. Log of the weight with the hat because it's still predicted. And then the log of the length. So suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part B to predict the fish. So here we're going to plug in 36 again for the length to try and figure out the weight. So we might need a little refresher on logarithms here because we're going to have to take the log. So you can just plug this in your calculator, log of 36, and then you can multiply it here, and then you can subtract this. And so you get to the log of the weight equals 2.8464. So I'm going to plug in my iPad and just give you a quick refresher on logarithms for how to do this next step. 10 of x equals 3. And the way a logarithm works is what you're saying is, I'm going to write this 10 just so you can see it. 10 to the power of 3 is x. 10 to the power of 3 is equal to x. So you can re-express this is one way to solve for x here, where you can say 10 to the power of 3 equals x. And so there you go. You know that x is 10 cubed. The other way you can do this is you can raise both sides to be powers of the base. So if I raise this to be, for example, 10 to the power of log of x and 3 to the power of 10. So should probably rewrite that. So I wrote it like this. Then what happens is the 10 cancels the log, and I'm left with x equals 10 cubed. So if you remember what I said, both ways end up with this result. But the best way to remember is really raise this, both sides, to be powers of whatever the base is. So in this case, the base was 10, so raise it to be the power of 10. The second thing that you'll come across in this lesson is the natural logarithm. So the natural logarithm, we have log with a base e. This is called the natural logarithm, and they don't write it like this. They don't write log base e. Instead, they write ln of x. So this ln is essentially log with a base e. So if I'm stuck with a problem, and we're going to see this in a second, if I'm stuck with a problem that looks like this, I have to raise both sides to be powers of e. And e is in case you didn't know, it's a number. It's kind of like pi. I forget what e actually is, 2.67 or something. It repeats forever. So e represents some number. So if I raise both these to be powers of e, then the natural log is going to cancel, and it's going to be x equals e squared. So this is how I can solve for x when it is trapped in a logarithm. So let's look back at the problem, and it'll make sense how they solve for it now. All right, so they had the log of the weight, and they're trying to solve for the weight. So they raised both sides to the power of 10. That's why this canceled the log, and we had 10 to this power, and that gives us our answer of 702.1 grams. So again, our predictions have been 688, 694, and now 702. So they're all relatively close, within 10 grams of each other about. All right, so we looked at power models, and power models are when x is raised to a power. Another type of model is when we have, it's called an exponential model, and it's when x is actually listed as an exponent. So those are the two types of models that we're working with here. And so we have a new set of data, and go ahead, take a second and read it. All right, so this is an exponential looking graph, and we're showing the number of transistors in billions based on the year. So as the years progress, the number of transistors drastically increases. So they re-expressed it, and you can see here they took the natural logarithm of the y variable, but they left the x variable the same. So based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and the years. Well, it looks linear. So since we don't have a residual plot, we can't talk about a residual plot. All we can do is look at the scatter plot and say, it looks to be strong, linear, positive relationship. So the model looks appropriate. The exponential model seems reasonable. So now they've given us the output, and just a reminder, they are going to show us, I guess they're not going to show us that they took the natural log of the transistors. So we have the year is x, so here's our slope, y-intercept is here, and we have to remember that we took the natural log of the transistors. So there is our regression equation, or linear model. And they want us to predict how many there will be in 2020. So we're going to plug in. We're actually going to plug in 50 this time, because that is 50 years after 1970. So this, remember, is the year since 1970. So 50 years after would be 2020. Plug it in, and you can do the multiplication. And then when you get here, you have to remember, you have to raise this to the power to be a power of e, and you have to raise this to be a power of e. And so that's why they have this value written like this. And e is a number on your calculator. If you hit second ln, that'll give you e as your the base. So this model predicts that an Intel chip will be made with about 68 billion transistors.